All right, so what I'm going to show here is that the area under or between what I'm going to show here is that the area between a V versus T curve and the t-axis represents a positive displacement. This is not obvious at all. So let's actually go through, kind of understand why this is the case. So if I look at a velocity time curve, it's there to draw it. And I wanted to know what the area was. What can I do? Well, I mean, clearly this is a curve. You can't really do much for this region, say this dotted region. Maybe I'll give this region a name. So for instance, I'll go and extend out my t-axis, and I'll call this point t sub I, and this is going to be called t sub I minus 1. And the whole I minus 1 and I is used for the purpose of partitioning this into a whole series of segments. Well, the idea is this. I can go and approximate this thing by some type of rectangle. So in other words, I'll go and take a rectangle. And the idea is that I should be able to find a rectangle who has the same exact area. Let's see. So I'll go and shrink this down. As you can see, to do this requires a little bit of nuance, because there's going to be some area in this rectangle that you're including under the curve and some area that you're excluding. So in other words, if you look at this, use a different color, we're including this area. We're including this area, but we're excluding this area. And so the idea is that you would actually go and adjust the height of this rectangle in such a way that the amount that you include is going to be equal to the amount that you exclude. It's a very nuanced type of idea, but it's doable. And so now let's actually find what the area of a rectangle is. I mean, it's pretty straightforward. You started learning this in like 6th grade. So how do you find the area of a rectangle? Well, it's going to be the height times the width. Well, the width is going to be equal to the change in t. So in other words, that width is going to be t sub I minus t sub I minus 1. What's the height? Well, that's not so obvious. Well, the height of this thing is going to equal this function evaluated at some point in between t sub I minus 1 and ti. So this is the point that it's being evaluated at. Let's actually give this a name. Let's call it, I don't know, ti star. And so the height of this thing is the height of the function at ti star. And the function, of course, is v. So this is v of ti star. So therefore, the area of this rectangle, which remember, we adjusted so that it's precisely the area under this curve. So the area under the curve is then going to be the area of that rectangle, which is v of ti star times this ti minus ti minus 1. And that's the area of, let's say, the ith rectangle, because we're going to do the same exact thing with all these other rectangles. So, for instance, this would be like this would be the I plus 1 rectangle, and this would be the I minus 1 rectangle. Sorry, I minus 1. Okay. Now we have the area. Now we're going to turn to a completely different problem. And this is what's kind of shocking. We're going to go to a completely different problem. Now we're going to go and look at a position versus time graph for this same exact phenomenon. And because this is going to be very difficult to figure out what the position is given that velocity, I just want to take a look at this region right here, the ith region. So in other words, this is happening over the same time period. So this is ti minus 1 and ti. And what I know is that in this time period, as you can see, the velocity is going basically from, the instantaneous velocity is going from some fixed value, right? Some constant fixed value, and it's increasing. So what you'd expect the position to be doing is increasing fast, like that. So now, at least in that region, I don't know what it's going to be doing in the other regions. It might be doing something like this, but we don't care about the rest of those regions. I just want to focus on this region, ti minus 1 to ti. So what we know from the prior class is that there's going to be a point in this interval between ti minus 1 and ti such that the secant line is equal to a line tangent to that point. In other words, there's about a point right around here, okay, such that the tangent line through that point is parallel to that secant line. Now remember, that secant line is the average velocity. The average velocity. The secant is the average velocity. Of the time interval. Ti minus 1 to ti. And so there's going to be some point, call it tau I, such that the instantaneous velocity at tau I is equal to the average velocity over that interval. Or more specifically, what that means is is that there's going to be a point, tau I, in that interval such that the instantaneous velocity, the slope of that tangent line, is equal to the average velocity. So now we need to actually take a close look at what average velocity is. Well, what is the average velocity? Well, in that time period, it's going to be the change in position. So change in position is going to be some x at ti minus x at ti minus 1 divided by the change in time, ti minus 1. And so therefore, what we have, and notice that's the average velocity of that time interval, called v bar I. And so therefore, what we have is the change in position in that time interval is equal to the instantaneous velocity at that point, tau I, times ti minus 1, or ti minus 1. So let's take a look. Hello. Hello. I'm recording a lesson. Okay. So, we're going to step back for a second. This should look familiar because in the previous case, what did we do? We found that the area of this rectangle is equal to v of ti star. And remember, ti star is an intermediate time between ti and ti minus 1. And that's the area of the rectangle. The displacement over that time period is equal to v of tau I times ti minus 1, which, by the way, is just called delta ti. That's your change in time. So I can now combine both of these. We have the area of the ith interval. The area of the ith interval is equal to v at ti star times delta ti, meaning the change in time of the ith interval. And we have the displacement, delta xi, is equal to v of tau I times delta ti. So now the question is, how are these two equal? In other words, if these two would be equal if these two functions were equal. Well, what we know is that ti star is intermediate between, it's some intermediate time point between ti and ti minus 1. And similarly, tau is the same deal. Some intermediate time point between ti minus 1 and ti. So how could we make those two velocities equal? Well, it's very simple. What you do is you shrink your delta ti. Or in other words, the way you would do this is by following the same exact procedure, but increasing the amount of subintervals for which you're evaluating this. So here's your total interval that you're finding the area of. And by increasing the number of subintervals, what's going to end up happening is, let me take this, move it a little bit. Oh, no. Let me erase this. What you're doing is by increasing the number of subintervals, you're letting V of tau I approach V of Ti star. Or in other words, what's happening is that basically there's nowhere for these velocities, these respective velocities to go but towards one another, because you're collapsing these intervals. So this is going to approach the slope of the corresponding tangent line. I hope that's clear. So therefore, what we have is we have the area is equal to the displacement over that interval.
So what it looks like is something like this. I'm going to open this up. As you can see, the number of subintervals over this range is increasing. And as it increases, it becomes a more and more accurate description of what the area is under the curve. It increases in accuracy, and each of these subintervals, the velocity with which the subinterval is being evaluated at, in other words, this velocity, is basically becoming more and more confined as your number of subintervals increase. And your number of subintervals increasing means each one of these delta t's decreases. So this velocity, or the velocity with which the point that it's being evaluated at, rapidly approaches the velocity that is intermediate between the endpoints of the two subintervals on the x versus t graph, which is why this all works.